Today we're diving into something that's all around you, but you probably don't even notice it. I'm talking about brazing. Think about your trusty bicycle frame, the complex network of pipes in your refrigerator or air conditioner, even some of the critical components in your car's engine. These things often rely on brazed joints to hold them together strong and secure. Brazing is one of those fundamental manufacturing processes that makes our modern world tick. So what exactly is this magical process called brazing? Well, it's not quite welding, and it's definitely not soldering. We use a special filler metal, which has a melting point lower than the base metals we're trying to join. The key here is that the base metals themselves don't melt. Only the filler metal liquefies, flows into the tiny gap between the parts through something called capillary action, and then solidifies to create a remarkably strong bond. Alright, let's talk about the star of our show today, heat. You simply cannot braze anything without applying some good old thermal energy. But here's the kicker, it's not just about cranking up the temperature until things glow cherry red. We're talking about heat, precisely applied. In the context of brazing, this careful application of heat is what we mean by heat treatment. It's about being a thermal surgeon, not a blacksmith swinging a fiery hammer wildly. This control is what separates a beautiful, strong joint from a lumpy, weak mess. Its main job is to raise the temperature of the base metals to a point where the filler metal will melt when it comes into contact with them. Crucially, this temperature must be the melting point of the base metals themselves. Proper heating reduces the viscosity of the molten filler, allowing capillary action to draw it deep into the tightest crevices of the joint, ensuring a complete and robust bond. The right amount of heat applied correctly can also help prepare the surfaces of the base metals for brazing. The heat activates the flux, allowing it to do its chemical cleaning work effectively. Okay team, we've established that controlled heat is non-negotiable for successful brazing. The next logical question is, how do we actually generate and apply this heat? One of the most common and accessible heat sources you'll encounter is the humble torch. These can range from simple propane or butane torches for hobbyist work and light-duty tasks, to more powerful MAP gas torches, and all the way up to oxyacetylene setups for when you need some serious BTUs. Torches offer great versatility and portability. You can manually direct the flame precisely where it's needed, making them ideal for repairs, one-off jobs, or situations where you need to heat localized areas. Then we move up to the big leagues with furnaces. Brazing furnaces are designed to provide highly uniform and controlled heating, which is absolutely critical for complex assemblies or high-volume production runs. Many advanced furnaces also offer controlled atmospheres like vacuum, nitrogen, or hydrogen, which can prevent oxidation of the parts during heating, sometimes even eliminating the need for flux. We also have induction heating, which uses electromagnetic fields to generate heat directly within the metal parts themselves. The brazing ballet: heating, melting, and cooling. So you've meticulously cleaned your parts, chosen your filler metal, selected your trusty heat source, and maybe even applied some flux. Now it's time for the main event, what I like to call the brazing ballet. The first act of our ballet is the heating phase. The primary goal here is to bring the base metals in the joint area up to the correct brazing temperature, uniformly and efficiently. Next up is the star turn, the melting and flowing of the brazing filler metal. As the base metals reach the predetermined brazing temperature, the filler metal, which has a lower melting point, begins to liquefy. Capillary action will draw the molten filler metal into the narrow gap between the faying surfaces. The final act in our brazing ballet is the cooling phase. Once the filler metal has fully flowed throughout the joint and you're confident you have a good fill, you remove the heat source. Goldilocks and the flame, the art of temperature control, and what happens when it goes wrong. Temperature control, my friends, is the absolute, undisputed monarch in the kingdom of brazing. It's not just about making things hot, it's about achieving that perfect, just right temperature, much like Goldilocks searching for her ideal bowl of porridge. If your temperature is too low, the brazing filler alloy simply won't melt properly. If the temperature is too high, you risk a whole host of other problems, from damaging the base metals to degrading the filler alloy itself. Cranking up the heat too much might seem like a good way to ensure the filler melts, but it can be incredibly destructive. Excessive temperatures can lead to the distortion or warping of your carefully prepared parts. On the flip side, insufficient heating is an equally troublesome foe. If you don't get the base metals hot enough, the filler alloy won't melt completely. Mastering heat in brazing is a journey, but the reward is strong, reliable joints every single time.